Let that neck go. Yo, we got the moves. That's a good chat load up. Yeah. Check. What a chat at, eh? What a chat at. Woo, feeling good. I like this one. Yo, Maham, Mr. Maham, he's here. Chat loaded up. Chat loaded up, chat. Mr. Maham, number one up top. Mr. Maham is the number one for today. Who's gonna take the number one spot for today? Woo, let's break it down. Little keys on this one. Woo! Alright. Welcome back, everybody. Hope everybody's having a great day so far. Welcome back into the stream. Welcome into the stream. I hope you're having a good afternoon or morning, wherever it is. Yes, I hope you guys are having a good day. How's work? It's good. We are halfway done with this lot of my product. So I specialize in this product that comes around. I build about 2 times a year, or sometimes 3 if we have a special order. Because it takes about from start to finish, in all like 3 months. But me actually, what I have to do probably about there's probably like a back end, like a month of planning, but even more so of that. But like actually building, probably like from pilot to end phase, probably like a good two months, right? And so it's a heavy investment, but it's a big payoff for the company. It's a big revenue source for the company and the site. So we're halfway there. Everything is looking good so far. What's up? All right, feeling good. Mr. Tim, Tiny Tim, Mr. Tim. He's back in here, Mr. Tim. Awesome to hear from you, Mr. Tim. Welcome back into the stream. Glad you could catch it. Tim's an old man. Tim goes to bed at like 9 o'clock. Can't stay very long. You gotta go to bed. All right, let's go ahead and get into the new course. Oh boy, are we ready for this? Geez, another repo coming up. Sheesh. Let's go ahead and go. This is MIT 6. MIT 6.002. All right, let's go ahead and make dir lecture 1. Let's go ahead and cd lecture 1. Let's go ahead and go. Let's go actually. Just go back 1 space with just 1 negative. Yeah. Let's go get it. Cool. Let's go get add. We don't have a source to push, right? Yeah, we know what files to commit. Cool. So let's go cd. We did lecture 1. Let's go ahead and touch lecture 1 nodes.md. Yeah. Let's cd back here. Let's code here. Look at us, neck beard and all. Look at us using the terminal. Grow out my neck beard just so I could use the terminal a little bit, huh? Look at me trying out the terminal. Might as well, right? While I have this here, I'm certified. Certified to use the terminal. Bro, 9 p.m. your time is literally 1 a.m. my time. This is rage bait. Just looking for those comments. Come on, keep coming. Comments, go. Feels good. Eduardo, welcome in, my guy. How's it going? Yeah, Tim in that Boston. He's in the Boston. He's from Mass. He's got a Mass accent. I can't do it. Okay, let's go ahead and get into this here. Let's go here. Okay. Let's get this set up here. Okay, I'm gonna want to record, right? For the replay. Okay. Should I keep chat up for the replay? I don't think I had chat on the screen last time we did a course. Yeah, the course is free. It's MIT OpenCourseWare 6.0002, Introduction to Computational Thinking and Data Science. It's going to be a good course to kind of bridge some gap between actually using our kind of more fluent Python abilities to kind of actually dive deeper into data science, computational thinking, and hopefully give us more of some sense of direction for maybe like a future of where to go from here in terms of rather than just kind of free floating and kind of making little random projects, maybe dedicating some more time into some more serious projects relating to some actual core fundamentals of computer science and whatnot. So that's kind of like the thinking I'm going with here. So let me know what you guys like about that. How do we want to set up the actual setup here? That's actually a good question. Oh, interesting. We have to kind of maybe figure out how to do this. So let's pull this over, and then I'll just pull this off, right? We don't need to see the... And then let's pull this over here. I guess that's fine. I just don't want to cut off information here. Let's go to the actual YouTube page here, and let's make this theater. Right. Let me know what you guys are working on. So, hello everybody, my name is Michael. Thanks so much for joining me here. Appreciate everybody hanging out. It's awesome to have everybody here. We are going to be jumping into this course. I'm 26 years old. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company where I make kind of advanced biological controls using kind of I do a lot of hand matrix formulation for actually developing theoretical yield for products and then executing them in the lab. So it's a pretty cool gig so far. It's fun. I like doing it. I'm kind of like a mid-level kind of scientist too. I lead products and teams, and it's a good time. And I've been doing that ever since I graduated back in 2021. Wow, time flies. Yeah, so cool. That's my background. I've been teaching myself how to code every single day for the past year about. I've been streaming, pretty much almost every single day with a day off here and there, when I, completely burn out and need just one day to just chill. But yeah, so I appreciate you guys being here. I code every single day after my 9 to 5 job as I teach myself things, and we're going to be jumping into a new course here that I kind of explained earlier. Let me go ahead and start my recording. I think I'm going to have to do like a little intro again. Sorry, you guys. Awkward. Just put me on mute, but all right, we're going to be diving into MIT OpenCourseWare, Introduction Optimization Problems, MIT 6.0002, Intro to Computational Thinking and Data Science. It's going to be a good lecture series. I hope you enjoy this series, and catch me on the stream if you want to follow along as we are live. All right, cool. That's a good enough intro for me. I'll chop it up. Nice. Cringe AF. Okay, moving on. Why don't you put your cam under the video? Well, that's a good idea. Well, I could make the video bigger maybe, right? The video is the most important part. I can make it as big as I want. I can make it all the way over here and just have my notes over here, which that's what I might do. Might just make my notes pretty small. Put them off to the side here. But that's pretty hard for you guys to read. This is that's pretty big. And then I could just kind of drag this up. We'll figure it out. I don't know. We'll figure it out. We will figure it out. That is for sure. Just go like that. All right, Charlie's here. We got Frozek. Yo. Anand, how's it going? I'm working on my final project for CS50P, 2:50 a.m. my time. Grinding. Let's go. Is this course second year grad level? This course is second year grad level. We're fried. I don't think so. I think it's probably like a pair between the intro to computer science course. It's like the second semester. Okay, here we go. Let's try to get into this.
Content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, welcome to 60002, or if you were in 600, the second half of 600. I'm John Guttag. Let me start with a few administrative things. What's the workload? There are problem sets. They'll all be programming problems, much in the style of 60001. And the goal, really twofold. The 60001 problem sets were mostly about you learning to be a programmer. A lot of that carries over. No one learns to be a programmer in half a semester.
No.
So a lot of it is to improve
maybe
your
some
skills,
of these YouTubers.
But also there's a lot more, I would say, conceptual, algorithmic material in 60002. And the problem sets are designed to help cement that as well as just to give you programming experience. Finger exercises, small things. If they're taking you more than 15 minutes, let us know. They really shouldn't. And they're generally designed to help you learn a single concept, usually a programming concept. Reading assignments in the textbooks.
This guy looks brutal.
I've already posted the first reading assignment.
Looks like he's going to give us some tough
And essentially, they should provide you a different take on the same material we're covering in lectures and recitations. We've tried to choose different examples for lectures than from the textbooks for the most part, so you get to see things in two slightly different ways. There'll be a final exam based upon all of the above. All right, prerequisites: experience writing object-oriented programs in Python, preferably Python 3.5. Familiarity with concepts of computational complexity. You'll see even in today's lecture, we'll be assuming that. Familiarity with some simple algorithms. If you took 60001 or you took the 60001 advanced standing exam, you'll be fine. Odds are you'll be fine anyway, but that's the safest way to do it. So the programming assignments are going to be a bit easier. At least that's what students have reported in the past, because there'll be more focus on the problem to be solved than on the actual programming. The lecture content more abstract.
So leak codes?
The lectures will be, and maybe I'm speaking euphemistically, a bit faster paced. So hang on to your seats.
Hanging on.
And the course is really less about programming and more about dipping your toe into the exotic world of data science. We do want you to hone your programming skills. There'll be a few additional bits of Python. Today, for example, we'll talk about Lambda abstraction.
Nice. Let me
inevitably some comments about software engineering, how to structure your code. More emphasis in using packages. Hopefully it will go a little bit smoother than in the last problem set in 60001. And finally, it's the old joke about programming that somebody walks up to a taxi driver in New York City and says, I'm lost, how do I get to Carnegie Hall? The taxi driver turns to the person and says, practice, practice, practice. And that's really the only way to learn to program is practice, practice, practice. The main topic of the course is what I think of as computational models. How do we
MIT
use
students
computation
are
to understand the world in which we live? So what is a model? To me, I think of it as an experimental device that can help us to either understand something that has happened, to sort of build a model that explains phenomena we see every day, or a model that will allow us to predict the future, something that hasn't happened. So you can think of, for example, a climate change model. We can build models that sort of explain how the climate has changed over the millennia. And then we can build probably a slightly different model that might predict what it will be like
in the future.
Yeah.
Okay. I got you, sir.
So essentially what's happening is science is moving out of the wet lab and into the computer. Increasingly, I'm sure you all see this, those of you who are science majors, an increasing reliance on computation rather than traditional experimentation. As we'll talk about, traditional experimentation is and will remain important, but now it has to really be supplemented by computation. We'll talk about three kinds of models: optimization models, statistical models, and simulation models. Let's talk first about optimization models. An optimization model is a very simple thing. We start with an objective function that's either to be maximized or minimized. So for example, if I'm going from New York to Boston, I might want to find a route by car or plane or train that minimizes the total travel time. So my objective function would be the number of minutes spent in transit getting from A to B. We then often have to layer on top of that objective function a set of constraints, sometimes empty, that we have to obey. So maybe the fastest way to get from New York to Boston is to take a plane, but I only have $100 to spend, so that option is off the table. So I have a constraint there on the amount of money I can spend. Or maybe I have to be in Boston before 5 p.m., And while the bus would get me there for $15, it won't get me there before 5. And so maybe what I'm left with is driving, something like that. So objective function, something you're either minimizing or maximizing, and a set of constraints that eliminate some solutions. And as we'll see, there's an asymmetry here. We handle these two things differently.
Okay. Nice.
We use these things all the time. I commute to work using Waze, which essentially is solving, not very well, I believe, an optimization problem to minimize my time from home to here. When you travel, maybe you log into various advisory programs that try and optimize things for you.
What's up with like the
they're all
1
over
second
the place.
flashes of the
Today,
PowerPoint?
you really can't avoid using an optimization algorithm as you get through life. All right, pretty abstract. Let's talk about a specific optimization problem called the knapsack problem. The first time I talked about the knapsack problem, I neglected to show a picture of a knapsack. And I was 10 minutes into it before I realized most of the class had no idea what a knapsack was. It's what we old people used to call a backpack. And they used to look more like that than they look today. So the knapsack problem involves, usually it's told in terms of a burglar who breaks into a house and wants to steal a bunch of stuff, but has a knapsack that will only hold a finite amount of stuff that he or she wishes to steal.
So you got to pick the right stuff to steal.
And so the burglar has to solve the optimization problem of stealing the stuff with the most value while obeying the constraint.
So you go for the jewels, the smallest stuff with the most value, right?
So we have an objective function.
You can't take that 60-inch plasma. Tim can't lift that thing out the... He's been sitting at his desk all day.
It has to fit in my backpack. And you can guess which of these might be the most valuable items here. So here's, in words, written words, what I just said orally. There's more stuff than you can carry, and you have to choose which stuff to take and which to leave behind. I should point out that there are two variants of it. There's the 0-1 knapsack problem and the continuous. So the 0-1, it would be illustrated by something like this. So the 0-1 knapsack problem means you either take the object or you don't. I take that whole gold bar or I take none of it. The continuous, or so-called fractional knapsack problem, says I can take pieces of it. So maybe if I've taken my gold bar and shaved it into gold dust, I then can say, well, the whole thing won't fit in, but I can fit in a part of it.
Why would you shave
the continuous knapsack problem is really boring. It's easy to solve. How do you think you would solve the continuous problem?
Does it fit? No. Does it fit? No. Does it
fit?
Yes.
Suppose you had over here a pile of gold and a pile of silver and a pile of raisins, and you wanted to maximize your value. Well, you'd fill up your knapsack with gold.
Then you go to silver.
And so you either ran out of gold or ran out of space.
Yeah.
If you haven't run out of space, you'll now put silver in until you run out of space. If you still haven't run out of space, well, then you'll take as many raisins as you can fit in. But you can solve it with what's called a greedy algorithm. And we'll talk much more about this as we go forward.
Greedy algorithm.
Where you take the best thing first as long as you can, and then you move on to the next thing. As we'll see, the 0-1 knapsack problem is much more complicated, because once you make a decision, it will affect the future decisions. All right, let's look at an example. And I should probably warn you, if you're hungry, this is not going to be a fun lecture.
Pretty hungry.
So here's my least favorite, because I always want to eat more than I'm supposed to eat.
What is that?
So
what's that ice cream in the bottom left?
Typically, knapsack problems are not physical knapsacks, but some conceptual idea. So let's say that I'm allowed 1,500 calories of food.
Okay.
And these are my options. I have to go about deciding, looking at this food, and it's interesting, again, there's things showing up on your screen that are not showing up on my screen, but they're harmless. Things like how my mouse works. Any rate, so I'm trying to take some fraction of this food, and it can't add up to more than 1,500 calories.
Yeah.
The problem might be
How many meals can you make?
once I take something that's 1,485 calories, I can't take anything else. Or maybe 1,200 calories, and everything else is more than 300. So once I take one thing, it constrains possible solutions. A greedy algorithm, as we'll see, is not guaranteed to give me the best answer. All right, let's look at a formalization of it. So each item is represented by a pair.
With the value,
the value of the item and the weight of the item.
Okay, right. The knapsack
And
can
let's
accommodate
assume the
items with a total
knapsack
weight of no more
can
than
accommodate items with a
W.
total weight of no more than W.
Okay, so you're just adding tuple pairs together of value
I
and weight.
apologize for the short
trying to
variable
maximize
names,
value to
but
get
they're easier to
the
fit
minimized
on,
weight,
on a slide.
right?
Finally, we're going to have a vector L of length n representing the set of available items. This is assuming we have n items to choose from. So each element of the vector represents an item.
Now, for those that have taken some more advanced mathematics with a more, or maybe the only kind of vector terminology I really know about is kind of in terms of physics. Now, he says of n items. Now, is he just kind of using vector as a synonym for array here to, house like, a vector of L, right? Let's go back to that. A vector L of length n represents a set of available items. So it's a set, right? So each item is distinct of its own, right? In that case, you can't, or maybe it's just a set of available. I'm not using set like a set terminology of each element of the vector is an item. Justin, hey Michael, you inspired me to start streaming my coding journey and my studies. Thank you. I'm going to start my first stream today. Hope you are well. Oh, nice, dude. I'll have to stop in and say what's up. That's awesome, my guy. A quantity having direction as well as magnitude. So a quantity having direction as well as magnitude, right? Okay. So how can we apply that to this then? Well, obviously there's magnitude in terms of like value, or even magnitude in terms of weight. However you look at these two variables applied to this vector, right, for each item. Right now, in terms of the weight is probably the length of it. Oh, he says, Mahan says, I think he means programming languages vectors like C++ that has pairs in it. So a list, I think. That's was my first interpretation, right? Kind of a length of n vector housing, containing n items, right? What do you guys think?
Representing the set of available items. This is assuming we have n items to choose from. So each element of the vector represents an item.
Okay.
Okay, so those are the items we have. And then another vector, v, is going to indicate whether or not an item was taken.
Okay.
So essentially, I'm going to use a binary number to represent the set of items I choose to take. For item 3, say, if bit 3 is 0, I'm not taking the item. If bit 3 is 1, then I am taking the item.
Okay, that's your constraint.
So it just shows I can now very nicely
if your
represent
items are
what I've
bits,
done by a
or
single
integers,
vector
right, of bits.
of zeros and ones. All right, let me pause for a second. Does anyone have any questions about this setup?
Okay, so what I think he was kind of getting at there is like he kind of threw this binary number example at you, but I think he was just representing using an example of like having the binary number be what you're trying to, you know, decipher in terms of like think of it as the family jewels that the robber is stealing in this knapsack problem, right? Where you have a constraint of this binary number. If the third bit is a 0, you take it and you apply it to this v vector, which indicates whether it's taken or not. So if it's 1, the item is taken. If it's 0, the item is, oh no, maybe not. So this is a vector v of length n is used to indicate whether or not items are taken. Oh, got you. So it is a binary number in itself, and then it just is a switch, right? So then you could give various kind of maybe create kind of codes to represent certain, you know, what you took and whatnot. And then, okay, I got you. So back it up. Back it up. So what this v vector is kind of like, is just a, so, right, all zeros at first. And if you take the item, you just flip that bit, like that represents the integer, or the index, sorry, for the L vector, which has the set of available items in it, and then as taken or not taken, right? Nice, okay, cool.
Indicate whether binary number to item. What I've done, so it just shows I can now, for a second, it's important to get, does anyone have any questions about this setup?
What's going on, Prism?
It's important to get this set up because what we're going to see now depends upon that setting in your head. Okay, so I've kind of used mathematics to describe the backpack problem. And that's typically the way we deal with these optimization problems. We start with some informal description, and then we translate them into a mathematical representation. So here it is. We're going to try and find a vector v that maximizes the sum of v sub I times I sub I. Now remember, what I sub I is the value of the item. V sub I is either 0 or 1.
Yeah.
So if I didn't take the item, I'm multiplying its value by 0, so it contributes nothing to the sum. If I did take the item, I'm multiplying its value by 1, so
you get the
value
back.
of the item gets added to the sum.
Easy.
So that tells me the value of v. And I want to get the most valuable v I can get.
Exactly.
Subject to the constraint.
Yep.
That if I look at the items dot weight and multiply it by v,
it's less than the total weight of
the sum of the
knapsack.
weights is no greater than w.
Nice.
So I'm playing the same trick with the values of multiplying each one by 0 or 1.
Yeah.
And that's my constraint.
Cool. I like that.
Make sense?
Yes.
All right. So now we have the problem formalized. How do we solve it? Well, the most obvious solution is brute force. I enumerate all possible combinations of items. That is to say, I generate all subsets of the items that are available. I don't know.
So let me just quickly pause this and say brute force. All right. Let's just get some, write down these notes here. Enumerate all possible combinations of items. That is to say, generate all subsets of the set subjects. This is called a sub. 2. Remove all of the combination whose total is and then 3 from the remaining value is the largest. Okay, cool. I think you might have given a definition of the greedy algorithm already, so I think I just need to apply it into here into the knapsack problem.
I don't know why it says subjects here, but we should have said items. Let me fix that. This is called the power set. So the power set of a set includes the empty subset. It includes the set that includes everything and every
Possible
thing in between. So subsets of size 1, subsets of size 2, etc. So now I've generated all possible sets of items. I can now go through and sum up the weights and remove all those sets that
exceed
way more than I'm allowed.
Yeah.
And then from the remaining combinations, choose any one whose value is the largest.
Yeah.
I say choose any one because there could be ties, in which case I don't care which I choose.
Yeah.
So it's pretty obvious that this is going to give you a correct answer. You're considering all possibilities and choosing a winner. Unfortunately, it's usually not very practical. What we see here is that's what the power set is if you have 100 vectors.
For example, if there are
Not
100
very
items to choose
practical,
from,
right?
the power set of the size
Even for a
is
fast computer, generating
right.
that many possibilities is going to take a rather long time. So kind of disappointing. We look at it and say, well, we got a brute force algorithm. It will solve the problem, but it'll take too long. We can't actually do it. 100 is a pretty small number, right? We often end up solving optimization problems where n is something closer to 1,000, sometimes even 1,000,000. Clearly, brute force isn't going to work. Mm-hmm. So that raises the next question. Are we just being stupid? Is there a better algorithm that I should have showed you? I shouldn't say we. Am I just being stupid? Is there a better algorithm that would have given us the answer?
Probably.
The sad answer to that is no.
Oh.
For the knapsack problem, and indeed many optimization problems, are inherently exponential. What that means is there is no algorithm that provides an exact solution to this problem whose worst case running time is not exponential in the number of items. All right? It is an exponentially hard problem. There is no really good solution.
You could tell this guy just thinks this is funny.
That should not make you sad. Because while there's no perfect solution, we're going to look at a couple of really very good solutions that will make this poor woman a happier person. So let's start with the greedy algorithm. I already talked to you about greedy algorithms. So it could hardly be simpler. We say, while the knapsack is not full, put the best available item into the knapsack.
Yeah. Always choose the best available, I can't spell this, item if the knapsack is not full.
When it's full, we're done. We do need to ask a question. What does best mean? Is the best item the most valuable?
That's a good question.
Is it the least expensive in terms of, say, the
weight
fewest calories?
Per calorie,
in my case?
right?
Or is
Weight.
it the highest ratio of value to units?
Yeah, like ratio.
Maybe I think a calorie in a glass of beer is worth more than a calorie in a bar of chocolate. Maybe vice versa. Which gets me to a concrete example. So you're about to sit down to a meal. You know how much you value the various different foods. For example, maybe you like donuts more than you like apples. You have a calorie budget, and here we're going to have a fairly austere budget. It's only one meal, it's not the whole day, of 750 calories. And we're going to have to go through menus and choose what to eat. That is, as we've seen, a knapsack problem. They should probably have a knapsack solver at every McDonald's and Burger King. So here's a menu I just made up of wine, beer, pizza, burger, fries, Coke, apples, and a donut. And the value I might place on each of these and the number of calories that actually are in each of these. And we're going to build a program that will find an optimal menu. And if you don't like this menu, you can run the program and change the values to be whatever you like. Well, as you saw, if you took 60001, we like to start with an abstract data type, like to organize our program around data abstractions. So I've got this class food. I can initialize things. I have a get value, a get cost.
Okay. So he has a class food, right, with initialization. He has a couple of variables that he assigns as class instance variables of self-name, values, and calories, which he takes in as a weight and a W, N, and V. So weight goes to calories, or W. So interesting that he just W, okay. So he's a get function, or just a getter for getting value and getting cost, and then density is just the ratio of the get function of the value to cost. Then he has a stir that prints out the name plus is less than the value. I can't read it behind this thing. Behind the closed caption.
Density, which is going to be the value divided by the cost, and then a string representation. So nothing here that you should not all be very familiar with.
Yep.
Then I'm going to have a function called build menu.
Build menu, here we go.
Which will take in
a list
of names. And
okay, it takes in, so names, values, and calories. Don't got any type hints on this guy. Okay, not using any type hints. Come on, prof. No type hints? Okay. Just give him a hard time. So we got names, values, and calories. So names, values, and calories are a list of same length. Name a list of strings, values, calories, a list of numbers. Returns a list of foods, right? So we have a menu for every I in the range of length of the values, right? So which is the same as the names and calories length as well. We're going to create a menu where we just have create a food item for each, and then we append that to the menu. Okay, easy.
And a list of values.
Not that we're not familiar with already.
Of equal length.
CS50P
and a list
Python.
of calories that are all the same length. And it will build the menu. Okay, so it's going to be a menu of tuples, a menu of foods rather. And I build each food by giving it its name, its value, and its caloric content.
Oh yeah.
Now I have a menu. Now comes the fun part. Here's an implementation of a greedy algorithm. I called it a flexible greedy, primarily because of this key function over.
So we have def greedy here, where we have items, max cost, and key function. Assumes items a list, right? Max cost is greater than or equal to 0. The key function maps elements of items to numbers. Items copy equals sorted. Okay, so we have items copy equals to assorted items with the key function, and then we reverse order is to set to true. So we set this to reverse being, I'm guessing they want the maximum up front given the key function, right, from descending. So result, total value is a cost. Total value and total cost are both equal to 0 for floats. For I in the range of the items copy, the amount of sorted items that we have, if the total cost plus the items copy index of I get cost, right, is less than or equal to the max cost, then we're going to append the item, and we're going to increase the total cost. Okay, so this just takes in basically every value in a linear format that you have it and adds it until you reach a max cost. Oh no, it takes every value that you can get, right? So this takes every value that doesn't exceed the max cost and that you can buy, and put in, then increases the total cost and total value.
Over here. So you'll notice in red, there's a parameter called key function.
Yeah.
That's going to map the elements of items to numbers. So it will be used to sort the items. So I want to sort them from best to worst. And this function will be used to tell me what I mean by best. So maybe key function will just return the value,
yeah.
or maybe it will return the weight, or maybe it will return some function of the density.
However you
of the density. But
decide to sort them.
The idea here is I want to use one greedy
I've
algorithm
implemented functions like this myself.
independently of my definition of best. So I use key function to define what I mean
in terms
by
of
best.
like custom sort, like in my projects.
So I'm going to come in, I'm going to sort it from best to worst. And then
Best to worst, yeah.
for I in range len of items sub copy, I'm being good. I've copied it. That's why I use sorted rather than sort. I don't want to have a side effect in the parameter. In general, it's not good hygiene to do that.
Okay.
And so I'll go through it in order from best to worst. And if the value is less than the maximum cost, if putting it in would keep me under the cost or not over the cost, I put it in.
Do I still have budget for it?
And I just do that until I can't put anything
Until
else
I'm over
in.
my budget.
So I might skip a few, because I might get to the point where there's only a few calories left and the next best item is over that budget, but maybe further down I'll find one that is not over it and put it in. Okay, that's why I can't exit as soon as I reach, as soon as I find an item that won't fit. And then I'll just return.
Coders heard the word hygiene, started shivering.
Does this make sense? Does
Yeah.
anyone have any doubts about whether this algorithm actually works?
Is this a trick question?
I hope not, because I think it does work. Let's ask the next question. How efficient do we think it is? What is the efficiency of this algorithm?
Well, it doesn't choose items based. It only chooses items based on the order that they're currently in, right? It doesn't selectively choose items. Well, actually, it only chooses items based on one certain parameter. Hey, we got a raid here with one viewer. Welcome in. We got a raid here. Thank you guys so much. It would completely just depend on what the order of the items was based on the key parameter that you put in, right? So you can't selectively put in, things, a combination of the two, maybe. Right? I appreciate it, Karabe.
Well,
it's a Karabe.
let's see where the time goes. It's the algorithm we just looked at. So I deleted the comment, so we'd have a little more room in the slide. Who wants to make a guess? By the way, this is the question, so please go answer the questions. We'll see how people do. But we can think about it as well together. Well, let's see where the time goes. The first thing is at the sort.
Always wanted
So
to know
I'm
about
going to
time.
sort all the items.
So you have to sort, right?
And
you have to lose, so n log n.
we heard from Professor Grimson how long the sort takes. See who remembers. Python uses something called timsort, which is a variant of something called quicksort, which has the same worst-case complexity as merge sort. And so we know that is
Log
n
n.
log n.
Come on, MIT students. N log n.
Where n, in this case, would be the len of items. OK?
MIT students, where are you at?
So
At the sort
we know
n
we
log
have
n.
that. Then we have a loop. How many times do we go through this loop?
N times.
Well, we go through the loop n times,
Come on, MIT
Once for
students.
each
Someone raise their
item.
hand.
because we do end up looking at every item. And if we know that, what's the order?
Was it O of n squared log n? Oh, no, just say
N log n plus
Plus
n,
n.
I guess, is order n log n, right?
Yeah.
So it's
You
pretty
just add the
efficient.
n so it gets right. It's not multiplication.
And we can do this for big numbers, like 1,000,000,
And then you drop the constant.
right? Log of 1,000,000 times 1,000,000 is not a very big number. So it's very efficient.
Tim Sawyer, hey. Tim, where you at,
All
Tim?
right. Here's some code that uses greedy. Takes in the items, the constraint, in this case will be the weight, and
And then just prints them out.
just calls greedy with the key function and prints what we have. So we're going to test greedies. I actually think I use 750 in the code, but we can use 800. It doesn't matter. And here's something we haven't seen before. So use greedy by value to allocate, and it calls test greedy with food, maxed units, and food.getValue. Notice it's passing the function. That's why it's not
This isn't
no
test.
closed parentheses after it. Use greedy to allocate it. And then we have something pretty interesting.
Lambda function.
What's going on with this lambda?
So we're calling for every value of x
So
basically
here,
this,
we're going to be using
in-place
greedy
function.
by density to allocate. Actually, sorry, this is greedy by cost.
One
And you'll
over
notice
cost.
what we're doing is we don't want to pass in the cost, right? Because we really want the opposite of the cost, right? We want to reverse the sort because we want the cheaper items to get chosen first, the ones that have fewer calories, not the ones that have more calories. As it happens, when I defined cost, I defined it in the obvious way, the total number of calories. So I could have gone and written another function to do it, but since it was so simple, I decided to do it in line. So let's talk about lambda and then come back to it. Lambda is used to create an anonymous function.
Yep, I know
Anonymous
this.
in the sense that it has no name. So you start with the keyword lambda. You then give it a sequence of identifiers and then some expression. What lambda does is it builds a function that evaluates that expression on those parameters and returns the result of evaluating the expression. So, and returns the result.
I want to write this down. Make sure I have it for you guys in the notes. right? Lambda functions are really good. I recently started getting more into like, making sure, trying to use them when I can rather than, not. I try my best to use them. I'm gonna use it like this. Right, and then, some expression.
Result of evaluating the expression.
Return to your function.
So instead of writing def, I have inline defined a function. So if we go back to it here, I have and returns the result of evaluating the expression. So instead of writing def, I have inline defined a function. So if we go back to it here, you can see that what I've done is lambda x, 1 divided by food.getCost
Of x.
of x.
Yep. So for every x, just map it to that value, right?
Notice food is the class name here. So I'm taking the function getCost from the class food, and I'm passing it the parameter x, which is going to be what? What's the type of x going to be?
The food item, right?
I can wait you out.
Come on, MIT.
What does the type of x have to be for this lambda expression to
A
make
food.
sense?
Dude.
Well, go back to the class food. What's the type of the argument of getCost?
Is it not a food?
What's the name of the argument to getCost? That's an easier question. All right, we'll go back and we'll look at it.
That was so trolling, man.
What's the type of the argument to getCost?
Self, a food.
Food, thank you.
Oh my gosh, dude. This is who's going and paying tuition? Dude. Not one person in that whole lecture hall knew that answer? What? This is MIT. 2016. This was before AI. You had a... What? Well, it's on the Clash of Clans in the back. Yo, this is crazy. If I was his professor, I would have walked out. I would have been like, yo, go back to 60001. Dude, that was actually crazy. That was like 30 seconds of solid lecture silence. Because no one knew the class object self was the call of a get function. Probably just didn't care.
We have a tradition in this class that people who answer questions correctly get rewarded with food. Oh.
It's like nailed him.
Napoli would have caught that.
Just decks the guy with the Laffy
All right,
Taffy.
so it has to be of type food, right?
Come on, this is
Itself
crazy.
In the class food.
Wow. Wild.
So if we go back to here, this x has to be of type food, right? And sure enough, when we use it, it will be. Let's now use it.
Don't bail him out, guys.
I should point out that
Don't bail him out. They didn't know.
Lambda can be really handy, as it is here. And it's possible to write amazing, beautiful, complicated Lambda expressions. And back in the good old days of 6001, people learned to do that. And then they learned that they shouldn't. My view on Lambda expressions is if I can't fit it in a single line, I just go write def and write a function definition, because it's easier
Solid
to debug.
advice. Solid advice.
But for one-liners, Lambda is great. All right.
I like this guy.
Let's look at using greedy. So here's this function test greedy. Takes foods in the maximum number of units. And it's going to go through, and it's going to test all 3 greedy algorithms.
Okay.
And we just saw that, and then here is the call of it. And so I picked up some names and the values. This is just the menu we saw. I'm going to build the menus, and then I'm going to call test greedies. So let's go look at the code that does this. So here you have it, or maybe you don't, because every time I switch applications, the Windows decides I don't want to show you the screen anyway. This really shouldn't be necessary.
I'm having fun. Y'all are making excuses
Key
for them.
changes.
I'm chilling.
Why it keeps forgetting, I don't know. Anyway,
It's only been like,
here's
it's been
the
like,
code.
we're almost done.
That's all the
We got
code
5
we
minutes
just looked
left.
at. Now let's run it.
I'm having fun learning this.
Well,
It's a good refresher.
what we see here is that we use greedy by value to allocate 750 calories, and it chooses the burger, the pizza, and the wine for a total of a value of 284. That's happiness points, if you will. On the other hand, if we use greedy by cost, I get 318 happiness points and a different menu. The apple, the wine, the cola, the beer, and the donut. I've lost the pizza and the burger.
Not a lot of healthy options there.
I guess this is what I signed up for when I put my preferences on. Oh, and here's another solution with 318. Apple wine, oh, yeah, all right. So I actually got the same solution, but it just found them in a different order, right? Why did it find them in a different order? Because the sort order was different. Because in this case, I was sorting by
Come on, man,
density.
add them to a set. Come on, dude, add them to a set. Why are we adding duplicate finds to the same thing? Add them to a set. Just return the set you found, and then, come on, man.
So from this, we see an important point about greedy algorithms, right? That we used the algorithm, and we got different answers. Why do we have different answers? The problem is that a greedy algorithm makes a sequence of local optimizations.
Delete code joke, Mahan.
Chooses
Delete
the
code joke.
locally optimal answer at every point. And that doesn't necessarily add up to a globally optimal answer. This is often illustrated by showing an example of, say, hill climbing.
All right.
So imagine you're in a terrain that looks something like this.
Gotcha.
And you want to get to the highest point you can get. So you might choose, as a greedy algorithm, if you can go up, go up. If you can't go up, you stop, right? So whenever you get a choice, you go up. And so if I start here, I could, right in the middle, maybe say, all right, it's not up, but it's not down either. So I'll go either left or right. And let's say I go right, so I come to here. And then I'll just make my way up till the top of the hill, making a locally optimal decision, head up at each point. And I'll get here, and I'll say, well, now any place I go takes me to a lower point, so I don't want to do it, right? Because the greedy algorithm says never go backwards.
So if you start at the other hill, though, you have a flaw.
On the other hand, if I had gone here for my first step,
I would have been going
then
down.
my next step up would take me up, up, up. I'd get to here, and I'd stop.
Yeah, because you can't go
and say,
down.
okay, no way to go but down. I don't want to go down. I'm done. And what I would find is I'm at a local maximum rather than a global maximum.
Yeah.
And that's the problem with greedy algorithms, that you can
Depending
get
on where you
stuck
start.
at a local optimal point and not get to the best one. Now, we could ask the question, what can I just say, don't worry about it, density, say, will always get me the best answer. I've tried a different experiment. Let's say I'm feeling expansive and I'm going to allow myself 1,000 calories. Well, here what we see is the winner will be greedy by value. Happens to find a better answer, 424 instead of 413. So there's no way to know in advance. Sometimes this definition of best might work, sometimes that might work, sometimes no definition of best will work, and you can't get to a good solution. Or you can get to a good solution, you can't get to an optimal solution with the greedy algorithm. On Wednesday, we'll talk about how do you actually guarantee finding an optimal solution in a better way than brute force. See you then.
See you then. Nice. Boom! That was Lecture 1, Introduction to Optimization Problems of MIT 6002, Intro to Computational Thinking and Data Science. Awesome, awesome lecture. That was really fun. I like him. He's a cool guy. And cool examples there of some good, object-oriented Python code that we were familiar with. So great lecture. That was fun. I enjoyed that one. If you guys enjoyed that one, leave a like on the stream. I am recording, so I will be uploading this to the channel as a watch-along series for our stream kind of breakdown. So awesome. I'll stop recording there. Sweet. Cool. So I think they do have some assignments, so we'll probably take a stab at these tomorrow. Nice. Feels good. How's everybody doing? I appreciate everybody being here and having and joining me. Welcome in. All right, so we just got done with that. We're approaching 9 p.m. my time. Still haven't had dinner yet, and I'm pretty hungry. So I'm kind of wanted to maybe potentially do an after-hour stream and do an after-hour stream and maybe stream some Counter-Strike. Right? I was thinking maybe trying it out and seeing what we could do. I don't know. We'll see if it'll work. I'd have to maybe do a test. I might do a test run tonight. Because I do need to try it out. And then what we'll have to do is make like an official launch once we get it all figured out, and then we'll open like 100 cases on stream. That'd be crazy. Dude, I want to open cases so bad. I've been waiting to do it with you guys though. So once we get like once we get it set up and figured out, and if I want to do the membership or not, like just $1 membership to watch the gaming streams, on the YouTube or whatever, because it kind of, I want to keep this channel more program oriented, so or whatnot rather than gaming. So I might make the gaming more of like an exclusive kind of whatnot, like kind of, and I don't want to say paywall kind of thing, but honestly that's what it is. But it's kind of more of like an extra content thing, rather than the free code learning, right? But yeah, I think that'd be fun. Or I might just, you know, say screw it and just go live and just do after-hour streams of us playing CS. I'm nervous to play though because you guys are gonna roast me if I can't clutch up or if I choke or like, you know, oh, it's gonna be so, dude, I'm not like that bad. I'm not that great. Like I'm silver, like I haven't played since I was like 17. Like it's been a long time. So, I mean, you just gotta cut me some slack. I have a gaming PC, so I got a new gaming PC here. I got from a custom builder in the area, and I'm excited to maybe give it a go with some streams. So it should be kind of fun. Um, should we should we try? If it gives me an easy, I'll do it. I don't want to do anything harder. It's Friday. I just, oh, dude, we solved the 100 problems on LeetCode, gents. Woo! Nice. What are the specs? Oh, let me read them off for you here. Specifications are um Ryzen 5 9600X, RTX 5070 Founders Edition. Got that NVIDIA plug, baby. I wanted to get that Founders Edition. 32 gigabytes DDR5. Got a gigabyte B650M gaming Wi-Fi MOBO. And a 1 terabyte NVMe SSD and 750 watt 80 plus gold power supply. And it's in a kind of a smaller form factor. I think it's ATX. Yeah. It's pretty good. It runs my CS at like 700, 600 frames. Pretty wide. It's pretty modern. It'll last me for quite a while. Founders Edition guy in here. Ah, yeah. My NVIDIA shares paid for that bad boy, so it's only fitting. I had to send it back a little bit. I had to give them a coffee, right? I had to show them some love, right? They paid for it. Oh, we got an easy. Okay. There's a bag. It consists of items. Each item has a number, 1, 0, or -1 written on it. You are given 4 non-negative integers, num1s, num0s, num-1s, and k. The bag initially contains what? Num1's items. So these are just integers. Oh, they word these problems so weird. We have a bag of items with numbers written on them. 1 1 0 0. 1 1 1 0 0. We take so 3 1s. Oh, okay. 3 1s, 2 zeros, 0 -1s. Got you. Then you can pick out 2 possible solutions. So what's the maximum sum you can get? Well, you can pick out 2 1s, right? Okay. Okay. So we just need to build a list based on the values in here and sort them, and then pick the K first slice off. Basically, is my approach, right? Right. So let's do this. We want to create a list. So we'll say ones is equal to a list of the value of 1 times num ones, right? And then we have, let's just duplicate this down, and this will be num zeros, and this will be 0, zeros, and then we'll copy this down, and we'll say neg1, we'll say negatives. Right, and then -1. Ones, zeros, and negatives, and we're going to say data is equal to ones plus. We want to pick them. Okay, so what if you actually just can we do it like mathematically rather? Like, can we take these? So we get like 3. Whatever. Right, and then we say return the sum of data up through k. Oh, no way. Let's go. Oh, first try. All right, there's obviously a better way. So rather than creating lists, and then taking a slice off, can I just exhaust these values first until I get, I just go like while num ones is greater than 0, we're going to k less equal by 1, and k greater than 0, right? We will reduce k down and reduce the num1's value down as well, but increase total by 1 here. And then we can copy this and do another loop here. So this should just be this would be O of n, right? Or not O of n. I don't know. It'd be O of these summed together, right? We would have to loop that many times. So this was the sum of this was n, right? So num zeros. We clear out our zeros, right? Reduce k. So we'll say, well, k greater than 0 here. And we'll do what Mahan always says to do. I always forget that we'll short circuit it and make k out front first, because that's going to be kind of our limiting factor here, right? And we'll say if num one's here, so we don't even have to do this additional well, I mean, never mind. We'll keep, and we'll say and here, right? And so then we don't need to increase total here. We'll just clear out our things, and then we'll say here, bring this down, num ones greater than 0. We'll reduce k down, reduce number of negative ones down, and then total plus equal -1, right? We'll reduce that down. So then at the end of this, we will just return total. So you'll just get caught in these loops, basically, right? Ooh. Five. Yeah, just some shares. Thunder. The maximum value. So first off, why doesn't this one work? I think we have like a minor bug somewhere. Increase filling. Don't do anything. Oh, number of zeros. Okay. So now if I use this test case, should I pass? Yes. Boom. Boom! Woo! Feeling good on this Friday, boys. Feeling good on this Friday. All right, can we do... Now, this does do some looping, right? Now, is there a better solution, right, where you can you use math, right, determine the maximum you can make across, right, just so if we sum together, right, let's look at our examples. So k is 2. So then if k is 4, you get 3. You can take 3 ones and 1 0. Yep. Now, is there any way that we can maybe take the values up front? But how can we, like, you obviously have to clear out values, right? What do you guys think? So we solved this one two ways here. First time we did it slow by just creating new lists, combining the lists together, summing the first slice, right? With the ones, zeros, and negatives out front. What is my cat doing? Kitty, why are you scratching the couch? What's your problem? What are you doing? I see you. Stop, knock it off. What you scratching the couch for? Who's scratching the back on the couch? Oh, cheers, lads, cheers. Mike, will you do higher studies in biochem in the future? Any research paper or publication? No, I actually never did any research. My stuff was more along the lines of like helping other students. Like I worked as a UTF undergraduate teaching fellow, so I ran all of the like study sessions for the like cram and finals and exams. And then I had open office hours a couple times a week for just personalized tutoring. And so I was employed by the university, like I was actually like an employee for Utah State. And then I was also a laboratory instructor where I was the only undergraduate with all the grad students that was running the undergraduate general chemistry labs where like I graded their assignments. I gave them their college grades, like I graded their lab reports and made sure like their yields and stuff. Hey, how's it going? Is it toughest without the U? Togust? How's it going? Thanks very much. I appreciate you, dude. Big fan of you. So I never did anything like with professors in terms of research and stuff. I know a lot of students went down that route. I kind of wanted to be paid for my stuff. I needed to pay for my college. I needed to make money. I'm not sure if they pay undergraduates in the research, like for research assistant roles. They might. And then we solved it this way. Right. This is the faster way here. Okay, let's go to the almighty orb here. Let's get some feedback. We always want to get feedback. Hello! Hello! I completed Leak Code 2600. It was pretty easy. I solved it in about 10 minutes, 2 separate ways. My first way is a little bit slower, and my second way is more optimized, period. I want you to take a peek at my code. Don't show me any code or change anything, but just talk me through your thinking and give me some feedback regarding my 2 approaches. Possibly poke at areas where I could improve. I am trying to think about a way I could solve this, just maybe mathematically or algebraically by, summing, the entire map together initially and doing some sort of operation on that in constant time. Let me know what you think. Yeah. Having like a date with GPT. Kind of nervous. All right. Nice job. LeetCode 2600 is one of those deceptively simple problems that invites you to think about both algorithmic clarity and mathematical elegance. While you're doing just that, let's break down your 2 approaches. Your instincts about optimization and whether your idea about a constant time summation has legs. Your first approach, greedy, procedural. While and this, right, your analysis, you're selecting greedily, take ones first, then zeros, then negative ones. This is exactly what the problem requires to maximize sum. Runtime, O of K in the worst case. That's crazy that it threw us a greedy problem just after we were watching MIT. That's actually crazy. That's nuts. We were taking notes on greedy algorithms and learning about them here with the knapsack problem example for optimization models. Wow. And LeetCode just read our mind. It's watching. It's watching. My leg. We gotta have like a my leg competition in the Discord. People gotta post their best sound bites of their my leg. I feel like I got a pretty good one. I'm not gonna lie. Finished. Initial watch of lecture 1. Cool. I'll go ahead and push these notes up to you guys on the GitHub when I make my Discord post here for the initial 60002 post. What you did well. Clear, clean logic. Anyone can follow it. Efficient and performant, especially in a constant constraint-heavy problem. Minor improvement opportunities. You're manually decrementing and checking bounds for each group. This is fine, but you could think in terms of min k group sizes to avoid. This is fine, but you could think in terms of the minimum between k and group size to avoid looping. Your second approach, constructive array-based. Correct, readable, and makes it obvious what the values are being chosen. You allocate O event space and copy and slice, which is unnecessary for a tight problem like this. What about a constant time math solution? It's solvable in a pure math without any loops or arrays. So you can take the minimum between k and the number of ones, then you can take the maximum between 0 and how many ones you took, right? So that's how much you have left, the difference. So either you have 0 or the difference, and then you take the minimum of those. Like you have none left or 5 zeros left. You take the maximum, 0. Ah, interesting. That's really cool, actually. So what you could do is say used ones is equal to the minimum between k and the number of ones, right? That's how many you can use, right? If you have k, you can use 2 ones and you have 3 left over, or you have 2 ones and k is larger than you used the 2 ones. Okay, then you say difference is equal to k less than the used ones, right? We could say used zeros is equal to the minimum of the maximum of 0 and the difference, and the minimum will be between the number of zeros, right? Then we recalculate a difference here to be diff less than the used zeros, and then we call used negatives is equal to the minimum of the max of 0 and diff and the number of negative ones, right? And then you return now. Is it summing anywhere in here? Because you don't need to do the amount of zeros, right? So you return just the amount of used ones plus use negatives, right? Because you don't need to multiply this by 1, but this would be but less than the amount of used negatives, right? Because it's a negative number. Yeah, you don't need to multiply 2 by 1. Doesn't matter. Boom. Cool. Always, yeah, min and max. That's a great way to do it. That's it. You nailed the algebraic constant time solution, and more importantly, you've reasoned it out properly. Let's talk to your logic and celebrate the precision. Used ones is the minimum between k and the number of ones. You take as many ones as possible first. Then you calculate a difference. Then you use zeros between the minimum of the maximum of 0 and the difference and the number of zeros, right? How many you have left, your new k, or 0, right? And you return used ones minus used negatives. So then you don't even need to do it for the zeros. Well, I feel like you might need to, all right? What's the drawing behind me? My girlfriend drew it on like one of our little, we had like a little drawing date thing. Yeah, we're getting to that. We're getting to the machine learning right now, Betchem. We're starting off with some. We will probably bust out this course pretty quickly. It doesn't seem too bad. This is only lecture 1, but we're gonna watch probably a lecture a day for the next 2 weeks or so. I might do 2 a day, maybe if on Saturdays or something. Whoops, my bad. On Saturdays or something, or Sundays to speed it along. But we'll do as we'll keep grinding it through, and then we'll move on to we're gonna do Sebastian, something or another, and a couple other those Coursera machine learning courses, and kind of dive into those. This is going to kind of warm us up to the idea of computational thinking and data science, and kind of get us some warm up into that idea with some good lectures from some good professors. Because at the end, the last 5 or so weeks get into machine learning here. Yeah, 11 through 15 are into machine learning and stuff. So it starts to kind of ease your way into it with some stuff, which is nice. So I think it'll be kind of a good transitionary course for us to kind of watch through and do as a stream here, which will be fun. And then we'll dive into some Coursera courses and all that jazz. All right, you guys, cool. We solved that leak code problem pretty quick. Sweet. We got 3 possible solutions on that one. We were able to come up with 2 ourselves. One that ran pretty quickly here. This was my solution. Interesting. And yeah, and then this one. Why does it show that? It's not this is my code here. All right, you guys. Thank you guys so much for being here. I possibly will come back on for a after hour stream. I'm gonna get some dinner here. I'm probably gonna go to the old T-Bell. It's Friday night, so I'm gonna treat myself with some junk, and gonna probably watch a show with my dog and give her some attention, and then I'm probably gonna hop back on and try to maybe do a test stream of a game of CS on my new computer, and we'll give it a shot and see if I have the bandwidth to do the package transfer to my MacBook, right, and stream it from my MacBook. So we'll see what I can do. Anyways, I'm gonna try it out. I'll see you guys potentially a little bit later. Have a great evening tonight, and I'll see you guys tomorrow. Where my girlfriend actually does come back tomorrow. She's been gone. If you guys haven't had to bail out and hang out with her for the past 2 weeks. She's been gone. So she's coming back tomorrow from a business trip. She does travel for business sometimes, and so she'll be back. And so I will try my best to make sure to keep the streams going. We're definitely going to keep going watching the lectures and stuff. But when she goes to the gym or maybe takes a nap because she's going to be pretty jet lagged, I'm going to hop on the stream. So just bear with me. It's Saturday already in Kenya. Nice, dude. It's Friday for me. It's crazy. You're in the future. My name is Michael. I appreciate you guys being here. I'm 26 years old. I have a degree in human bio and a minor in chemistry, and I work as a formulation chemist full-time, and I teach myself how to code afterwards. I appreciate you guys for being here. Please subscribe to the channel. I stream every single day that I can after my 9-to-5 job, and teaching myself how to code from scratch with books, courses, videos, resources, just anything I can, and obviously practice and building projects. So thank you guys so much for being here. Check out my website, michaeldeming.com, to see my projects and get quick access to all my communities and stuff, like Discord. And thank you guys so much for being here. I'll see you guys tomorrow.